First of all, thank you everybody for attending live from your couch afterwards. It is a great pleasure to have a webinar today about space interferometry from Joe Lazio. And I will do a little quick introduction about Joe in a second, but first a few housekeeping items for everybody. First of all, it will be great to increase bandwidth if everybody can turn off, other than Joe, turn off their video and their audio for now. Please use the chat feature at the bottom for any questions and I will bring them up. And at the end of the talk, during Q&A, everybody can bring up their audio and video so we can have that conversation. This is one of the many PIRE events, and I urge you to go to the PIRE website, bhpire.arizona.edu, to look for other events in the future and also recordings of past events for this. And for the participants, at the very end, you're going to receive a link with some short evaluation. This is very important for us because webinars is something that is new for our community, and we would like to get your input of how it worked in order to improve it. So if there's, as people are coming in, let me just say once more that it is my great pleasure to have Joe Lazio joining us today. Joe got his PhD in the previous millennium than most of us from Cornell, right?
Correct, yes.
Cornell University, and he is a very well-known radio astronomer, has done incredible amount of work on anything. The part that I got to know Joe is from pulsar work and the electron distribution model of the galaxy, but then he has moved on to better and bigger things. I know he's very involved with SKA. We're all very interested in, what will happen from that. But today he's going to talk to us about something completely different, which we all love, which is interferometry from space. So thank you very much, John. Please go ahead.
Thank you. It's a great pleasure and privilege to be able to give this presentation. And let's see. Now I've got to figure out how to advance my, there, okay. So what I'm going to do is provide a bit of an introduction and historical background to interferometry and space interferometry. I'm going to provide some heuristic motivations for interferometry so that people are not left saying interfero what, and then look toward the future with some science motivations for potential missions, and actually potential missions that are being discussed right now. My intent is at the end of this presentation, you'll have some heuristic understanding of interferometry. It'll be heuristic and how you can construct large synthetic telescopes. You'll have some appreciation for the science motivations for future space telescopes or future space missions, and an appreciation of the importance of doing multi-wavelength astronomy or astronomy at many different colors of light, other than the ones that our eyes can see. And so in particular with respect to the interferometry, let me go back to that first objective. This picture in the upper right has gotten a lot of attention in the past week or so. And I hope that you'll have a sense of, again, a heuristic understanding at least of some of the details going into that. Demetrius has already given a bit of an introduction, but the aside of who I am, my current role, the simple way to say it is I'm chief scientist of NASA's Deep Space Network. I'm the kid who always wanted to grow up to be a radio astronomer and actually am. And then have been involved in a bunch of ground-based telescopes and current project scientist on a space-based interferometer concept that's under consideration by NASA. Now, if we start with the most obvious optical instrument, that's our human eye, the one that's been known since antiquity. And if I hold a quarter up on the opposite side of a football pitch, and you have roughly 20/20 vision or normal unaided vision, you would be able to tell that I'm holding up a round object. And what, in an astronomy context, what we'd say is our eyes have a diffraction limited capability, or they're capable of looking at objects that are about an arc minute in size and distinguishing those as real objects. Even a modest optical telescope, so what you see here is a picture or a reproduction of Galileo's telescope. Even a modest optical telescope provides about 60 times better angular resolution than that. And I'll just remind you, there are 360 degrees in a circle. The ancient Babylonians, and we astronomers continue to use this practice, the ancient Babylonians divided a degree into 60 subdivisions, which we call arc minutes. And then each arc minute is further subdivided into 60 subdivisions called arc seconds. Okay, a long-standing question in astronomy. very basic, is can you split two stars? Can you tell that there are in fact two stars in the sky very close together? A classic vision test known since antiquity is if you look at the Big Dipper, in the handle of the Big Dipper, there is a star that is in fact two stars. And the question is, if how good your vision is a question of how well you can separate that in fact one of the stars in the handle of the Big Dipper is in fact two stars. Very basic optics, freshman level physics or so. We can write down, and I'm not sure if you can see my cursor, but we can write down the angle, how close two things can be on the sky. And that determines, that's one measure of how good, say, your eye or a telescope works, is dependent upon two quantities. One is the observing wavelength, or essentially the color of light at which the telescope is operating. And the other is the diameter of the telescope, how big is it? If we just do this for the human eye works very well at about in sort of the green-yellow light, which is where the sun puts out most of its radiation. And that's a wavelength of like 550 nanometers or that many millimeters. Your pupil at normal operation it has a diameter of something like 5 millimeters. And if you just divide those two numbers, you end up with a number of something like 0.0063 degrees, or a little under half an arc minute, which to astronomical accuracy is about the arc minute I said earlier. So a typical human eye, if two stars are on the sky separated by no more than about an arc minute, we can still tell that they're two, in unaided vision, you can tell that there are two stars there. And before I go on too much further, again, just to make sure everybody's on the same page, this is the electromagnetic spectrum. So the visible light that our eyes respond to, the red, orange, yellow, green, blue, violet, that's a very small sliver of the entire spectrum of light. And I often describe it as there are many colors of light that our eyes simply cannot see. If you go to wavelengths shorter than visible light, so the curvy thing here is supposed to be a schematic of the wavelength of the light corresponding to the different colors. If you go to shorter wavelengths, well, in fact, a little bit of ultraviolet light gets through the Earth's atmosphere, and if you've ever had a sunburn, you've experienced the effects of that. If you've ever had a dental or some kind of X-ray, those are even shorter wavelengths of light. You can then go the other way as well to colors of light that are more red than red, so that gets us into the infrared. And if you keep going to even longer wavelengths, you go to microwave and radio. The other important thing on this diagram is that this portion here, if you can see, the part of the spectrum that's the visible light comes through the Earth's atmosphere very nicely, which is perhaps not surprising that our eyes work there. Some of these other colors of light or some of these other wavelengths of light, like ultraviolet and an X-ray, do not penetrate the Earth's atmosphere, with very small exceptions in the ultraviolet, which is actually a good thing because otherwise it'd be problematic for life on the planet. Also, in the infrared, the atmosphere is partially opaque or completely opaque. And then once again, down at the radio wavelengths, it opens up and we can see out through the Earth's atmosphere. So one of the motivations for space missions is simply to get above all of this obscuration at different wavelengths. Also, I'm going to focus mostly on the radio window for a couple reasons. One is, as Demetrius indicated, it's substantially my background. It's also interferometry. This concept is most mature there. It's in part because of the wavelengths of light and the fact that they make it through the Earth's atmosphere. But just to drive home this point, why do we astronomers look at all these different colors of light? This is an image, a composite image of a cluster of galaxies. So all the little yellow and white things you see there are galaxies of billions of stars. The blue light here is actually color-coded blue. It's the X-ray emission from the gas that enshrouds all of these galaxies. And in fact, there's more mass in the gas that's producing this X-ray emission than there are in all the stars in the galaxy. And these red things here, these are the radio emission that is being generated by this central galaxy, carving its way out through the gas, the X-ray emitting gas. And you can start to appreciate, I hope, with this one picture of why astronomers are so enthusiastic about looking at all these different wavelengths of light. You get a substantially different picture of this cluster of galaxies and the physics that's happening, depending upon which wavelength of light you use. And it's only when you put them all together that you really get a coherent picture. Okay, so on to this interferometry stuff, or interfere what? So what is it? Let's look at the Arecibo Telescope, which is the second largest radio telescope on the planet. And I'm going to use as a notional wavelength of operation 30 centimeters or 0.3 meters. And Arecibo is an impressive telescope. It's 300 meters across. And if we just run through that little equation that I did earlier, you've already probably read the slide. The Arecibo telescope has an angular resolution, a capability to distinguish 2 points on the sky of about 0.06 degrees, or about 3 arc minutes. So the astounding thing is that this radio telescope, that's 1/3 of a kilometer across, has poorer angular resolution than your eye. How would we solve this? I mean, if you just ask the question, how do I build a radio telescope that is even approaching the capability of the human eye? Well, you run through that equation again, and you'd need a telescope that's something like 1 kilometer across. And if I want to match the angular resolution of even modest visible wavelength telescopes, something akin to what Galileo had or that era, I need a telescope that's 10 kilometers across. Now, ignore the cost of the metal. It's just an incredible engineering challenge. How would you even build, how would you carpet part of the planet with 10 kilometers of metal? It's an impressive engineering question. However, let me blow up the Arecibo telescope a little bit more, and you notice that there's a hole in the middle of it. And that sort of begs an interesting question. How many holes can you put in a telescope and still have it work? So to answer that question, I first have to ask another one, which is just basically, how do telescopes work? So all telescopes, whether they be radio or optical, ultraviolet, infrared, and even to some extent X-ray, the idea is that you have incoming light and it reflects off a reflecting surface, and you bring it together at a point. And the rays of incoming light all come together at the same time. So in fact, an exercise that I'll leave for the reader is, it's an interesting exercise in either geometry or calculus or some sort of freshman level calculus, is if you take a parabolic surface and you shoot light rays at it, all traveling at the speed of light, you can show analytically or precisely that they all arrive at a point at the same time. Now, in fact, for extra credit, Arecibo is actually part of a sphere. So if you repeat that for a surface or a section of a sphere such as Arecibo, you actually end up with line focus. But this sort of raises an interesting possibility. If I can get reflections from a number of different reflecting surfaces all at the same time and bring them together at the same time, then I can build a telescope. So here's an example. If I can take signals that hit individual antennas or individual telescopes and then bring them together at the same time, or we would say coherently, then I can effectively synthesize an aperture. I can synthesize a telescope that is as big as the separation between the individual antennas, or I can build a telescope that's mostly holes, or a holy telescope, if you will. So the next little bit of this conversation or lecture is, what's some of the mathematical background? And I'm not going to do it rigorously. I'm going to attempt to give you the heuristic flavor of it. So let's look at, we have 2 antennas, which are separated here by this baseline that I'm calling B. And we have a bunch of incident light rays. Now remember, light is an electromagnetic wave. So you think of a peak and then a trough and a peak and a trough. So imagine that these light rays are tracing out part of the peak. And I can replace that by a wavefront. I've got an incident wavefront coming in, and clearly the wavefront is going to hit this telescope earlier than it hits this telescope, or it's going to hit the telescope on the right earlier than it hits the telescope on the left, because the wavefront, in order to get to the telescope on the left, it has to travel this slight additional distance, which I've labeled X. And of course, it depends upon this angle psi, what angle the radiation is coming in. So this is a simple trigonometric problem, high school trigonometry. What is that extra path length? And that extra path length is given by the sine of this angle psi and this baseline B, the separation between the 2 antennas. And then if I consider, well, it's an electromagnetic radiation or it's light, so it's traveling at the speed of light, that means there's a delay. There's a geometric delay between when the radiation hits this first telescope on the right and the other telescope on the left. And now you can start to see where I'm headed with this. If there's a way of capturing the signals here at the right telescope and then delaying them by an amount tau, that's the geometric delay, I effectively bring this wavefront as if it hit the 2 telescopes together at the same time. And I'll pause here for a moment. One of the powerful reasons that we can do this so well in radio astronomy, and why radio interferometry is so mature, Here's a conceptual radio telescope. You have some collector. It's very faint radio. Actually, in general, the universe is very faint, so that's why astronomers are always after bigger and bigger apertures. We amplify the signal. Often we filter it. In recent decades, we can digitize it, but the important thing is that we can record it. We can actually record the signal for later playback in one form or another. So this playback, this inserting the delay, can actually happen days or even weeks or months later. Okay, this has already, however, illustrated a couple of fundamental aspects of interferometry, and they're important for the space, they're really important for the space context. I've got an incident wavefront, I need to insert a delay, and that delay depends upon what the separation between the antennas are. I need to know where the antennas are. I don't need to control them. So as long as I know where they are, I can insert this delay, calculate this delay, and then insert the delay. But from a space context, I don't actually have to position. If you move the antennas, but I know where they are still, I can still insert the appropriate delay. The other aspect is you can imagine if I pick all of these telescopes up and simply move them to the left by a meter, nothing changes. The only important aspect in all of this is the relative position. What is the relative separation between the antennas, not their precise absolute location. Okay, let me go a little bit more deeply now into the math. So I'm taking the signals that are hitting one antenna, which I'm going to represent as a sine wave, and I'm taking the signals that are hitting another antenna, separated by some baseline B, that are also a sine wave. I'm adding, or in this case, I'm inserting a delay and multiplying them together so that if I've inserted the correct delay, it's as if they hit the two telescopes at the same time, and I'm essentially bringing them into focus. Okay, so I've got a geometric delay, which is what we've written down before. Here is the output when I do this delay and then multiplication of the sine waves from the two different antennas. This is the output, or this is essentially the output of the interferometer. Now, this is actually a trigonometric identity. If you go look in a mathematical handbook or maybe a trigonometric textbook, you can see that the product of two sines is a trigonometric identity. So we can just write that out. And again, I've done nothing here other than write out a trigonometric identity. But now suppose I take an average. This frequency here, the frequency of light at which we're concerned, certainly in the radio, a typical frequency might be a gigahertz, which means there are a billion radio waves that pass over the telescope every second. So if we average for even a small amount of time, this product, nu times t, it can be a very large number. Okay, well, if we just take the sine squared of a very large number, if we average, it turns into a half. So this first term, this sine squared term, is a half. The sine or the cosine of a big number averages to 0. So the second term goes away. And we are left with the output of this interferometer, the product of these two, the signals from these two telescopes, is nothing more than a cosine function. And now I can rewrite it. I've just rewritten it, replacing instead of the geometric delay, I've replaced by actually putting in what the baseline and the wavelength is. Okay, so it looks something, here's our interferometer now. This is essentially the basics. So there's a geometric delay. We take the output of those signals, we do a little bit of averaging, and voila, we end up with a cosinusoidal function. Just standard lingo, very often you will hear radio astronomers refer to U. U is nothing more than the length of the baseline, the separation between the two antennas measured in wavelengths. And for reasons that well, I think I'll probably gloss over mostly, I'm just going to replace the sine angle here with the angle itself and call it L. Now, it would be a pretty boring universe if there's only one incident wavefront, if there's only one source in the entire sky. And in fact, the interferometer is capturing wavefronts coming in from all different directions. So a more appropriate way to write this would be as the sum over all of the incident angles of this cosinusoidal function. And I've glossed over a little bit of the technical details here, but essentially the output of an interferometer is this sum of cosinusoidal angles, or cosinusoidal functions rather. And if you've had maybe a little bit of advanced calculus or something, you might be starting to get suspicious as this looks very much like a Fourier transform. In fact, your suspicions would be correct. So I've sort of tried to motivate heuristically that the output of an interferometer, it has some cosinusoidal function or sinusoidal function, and there's a sum. There are whole chapters written, but essentially you can write this down mathematically in a very rigorous sense, that there's a Fourier transform relation between what the interferometer measures and what we really want to know. So this is called the Van Sittert-Zernike theorem. And again, I put it up there only to suggest that there is a rigorous mathematical underpinning, and I've only tried to give you the heuristics. What we'd really like to know is the sky brightness. So this sky brightness, the I, the intensity, is how bright the sky is as a function of different angles, L and M. And then what the interferometer measures, formally is called a mutual coherence function. In the lingo, we often call it a visibility function. And there's a relation between what the interferometer measures, the visibility function, and what we want to know, and it's a simple Fourier transform. Now, I've glossed over some details here in terms of some assumptions that underpin writing it down this way, and some of modern interferometry is involved in relaxing those assumptions or figuring out cases in which they don't apply. But for the moment, the key thing is that there's a Fourier transform relation, which, again, you can think about heuristically. What does that mean? It means that the baseline, or the separation between the two antennas, and the angles that we measure on the sky are Fourier conjugates, or that if I get really long baselines, I can measure really small angles on the sky. Now remember where we started with all this. I just said, what is the angular resolution? What is the angle that we can see on the sky? How well can we split two stars, say? Which was a wavelength over an aperture. Well, if all I have to do is redefine what this angle is, and I've used different symbols for what the aperture diameter or the baselines are, but effectively you can see the relationship now that if I have very long baselines, I've effectively synthesized a very large aperture, and therefore I get very fine angles on the sky. So the midterm review here is key things for an interferometer are the antenna separation measured in wavelengths is essentially the aperture diameter. How big you can make your baselines, or how your antenna separations are, what your antenna separations are determines what that angular resolution is. You might suspect that depending upon how we actually distribute the antennas, there's some effect on the performance of our synthetic aperture, and you'd be correct, there is no free lunch. And particularly in the space context, the relative antenna separations are really, really important. You need to know what they are. You do not necessarily need to control them. Again, this has been well developed over the past 50 plus, maybe even 60 plus years in astronomy. The 1974 Nobel Prize Physics was awarded in part to Sir Martin Ryle for his work. But of course, again, as in many things as science, Sir Martin Ryle did a lot of work, but he built on the foundation of many people coming out of World War II when there was a lot of leftover radar equipment. Now, I've already sort of written down some of this stuff. The baselines determine the angular resolution, or how fine of an angle we can see on the sky, how small of an object we can see on the sky. And again, the basic idea is large antenna separations, large baselines mean small angular resolutions, or very fine angles on the sky. I want to point out one interesting aspect of an interferometer, which is unique to interferometers, is not true of other kinds of telescopes, like maybe the Hubble telescope or a big optical telescope with which you might be more familiar. I've been focusing on the big baselines, but there are clearly small baselines in here too. There are antennas that are very close together, but there's a limit to how close you can pack the antennas. There is just fundamentally, you don't want the antennas running into each other, or you can't pack them too close. And what that means is that there's a smallest baseline that we measure. And if there are any angles on the sky that correspond to even smaller baselines, we don't measure them, and we can't see them. The lingo is that the source is resolved out. Effectively, it disappears from view. So very big sources, there's some typical largest angular scale that any interferometer can see, and anything bigger than that just completely disappears from view. And this is unique to interferometers. It's also, it can be important when interpreting images. But this is the basic concept now. I have a bunch of antennas, and actually I've done all of this in the radio. I'll get back to it a little bit later. You can do this at any other wavelength you'd like as well. But I have a bunch of antennas, and you take all of the unique pairs, 1 to 2, 1 to 3, 1 to 4, so on and so forth. You delay the signals appropriately, multiply them together. You come up with a visibility function or a mutual coherence function, and then all you do is simply Fourier transform it. And of course, there are technical details, but that's the basic idea. We can actually, this telescope that I'm showing you here is the Very Large Array. So if you're in Arizona, in fact, in Tucson, it's only sort of 6-hour drive east, or it's sort of a 6-hour drive east from Arizona to get to New Mexico to this telescope. This is what it looks like in an interferometric sense. So each one of these blue points that you see here is a measurement, one of these measurements of this visibility function or this mutual coherence function. And just for reference, actually let me back up. So you can measure the separation between two antennas in an X and a Y plane on, say, on the surface of the Earth. And in interferometric lingo, we call those U and V, but they're essentially just the X and Y coordinates of each telescope as measured in wavelengths. And you can see that the scale here is something of order 40,000. The largest baselines are 40,000, or they're 40,000 wavelengths. This particular observation was at a wavelength of 6 centimeters, which means the baselines involved were sort of like 2.4 kilometers in scale. And again, remember where we started with all this. I said, if I want to be able to have a telescope, a radio telescope, with an angular resolution, with a capability similar to modest optical telescopes, I need kilometer scale baselines. And that's essentially what we've now constructed. You might notice the VLA, this particular telescope, is in the shape of a Y. And the plot here with each point representing one of those pairs of antennas where the signals have been multiplied together, you clearly see a Y structure, but it actually, it's a star-shaped structure, as if it's two Ys. And that's, again, one of these fundamental aspects of the intensity that we are measuring on the sky is a real quantity, real in the sense of complex numbers. That imposes certain symmetries on what we actually measure, that there are certain relationships or symmetries that the visibility function, the mutual coherence function, must obey. So the reason that you're seeing a star pattern here is every time we make a measurement at one point, for one set of antennas, we effectively get a separate reflection of that in this particular plane or in this particular representation. But effectively now, here you're looking at our synthetic, you can imagine it as if we're looking at our synthetic aperture. This is a snapshot. So this is as if taking on, say, a 1 second or a 10-second basis, one measurement. As the Earth rotates, and this is actually something you can try at home, you can just draw a line on a globe and then spin the globe, and what you'll see is as the Earth rotates, that line will appear to change in length as it goes in and out of view. So if you take measurements over time, you can actually build up a more complete synthetic aperture. Each one of these little curves here that you see is a separate measurement at a different point in time, watching as the Earth rotates. This is also sometimes called Earth rotation synthesis. But the idea is that we can help fill in our synthetic array, not by adding more antennas, but simply by having them move around appropriately. In this case, all of the antennas are on the ground, so it's determined by how the Earth rotates. If I now Fourier transform these measurements, remember all I'm doing here is sort of taking cosines and sines. This is now how well my interferometer works. So this little spot at the center is a measure of the angular resolution. If there are two radio sources on the sky, and actually let me back up here for a second. So this measurement here, this set of data here are U's and V's, or baselines measured in wavelengths. If I Fourier transform them, remember U and V are conjugate pairs with angles on the sky, I turn into something that has angles on the sky, and sure enough, that's measured in arc seconds. And I said that this would have an angular resolution of, say, 5 arc seconds, several arc seconds. You can see that the size of this white spot, which is a measure of how good the angular resolution is, that spot is a few arc seconds in size. So this is a demonstration of here's how close two things could be on the sky. They could be a few arc seconds apart, and yet this interferometer could distinguish them. If they're much closer than a few arc seconds, this interferometer could not. All of this other stuff that you see out here, this reflects the fact that the telescope remains mostly holes. So when you look at actually doing the mathematical Fourier relations, all of this other coloring out here, all this other grayscale out here, represents that the interferometer, the synthetic aperture, still has a angle. It actually responds to sources that are far away from where you're exactly pointing, which leads to some interesting aspects in terms of processing. I'm not going to get into it because of time and technical issues, but effectively this is a side lobe. We call them side lobes, and they are a measure of how big the side lobes are as a measure of how good the telescope is, the synthetic telescope is. I've been showing a lot of pictures of this very large array. You may have noticed, in fact, that there are what appear to be railroad tracks running through it. Those are actual real railroad tracks. So in the case of the VLA, the antennas can be moved around. You can pick them up and move them around. In this particular case, this is the most compact configuration that the antennas are separated. The maximum separation is about 1 kilometer. The antennas, or the railroad tracks, run out about 20 kilometers to make a roughly 30-kilometer diameter antenna, or synthetic aperture. You could ask, by this point, you're probably asking an obvious question, well, how big could I make an interferometer? And one of the reasons I'm in radio astronomy is because this was a really cool thing when I was digesting, well, I was devouring all the books in my public library. This concept can be extended to the entire planet. Here on the left is the Very Long Baseline Array. On the right is, on the right is the European VLBI network. But if you can know where the antennas are, calculate the appropriate delay, record the signals, and then play them back later, or somehow bring all of the signals back together and play them back with the appropriate delays inserted, you can construct a synthetic aperture that's as big as a continent, say North America. Or in the case of the European VLBI network, the EVN, you can see that although they started in Europe, they've since expanded to China and Africa and even to the island of Arecibo, so that effectively a planet scale interferometer can be constructed. Okay, do we have to stop there? And as you might guess, the answer is no. Very early on, when people were doing these measurements with terrestrial Earth-size baselines, and even when the interferometers were much smaller, say 5 antennas or something, it became clear that even on terrestrial baselines, even when you were synthesizing a telescope that's comparable in scale to the size of the Earth, there are still some radio sources that are unresolved, or effectively look like point sources. You couldn't tell if there was 1 or 2 sources in there. So this is a modern movie example. What you see here, again, this is position on the sky, now measured in milli-arc seconds, thousands of an arc second. And this bright blob here, this bright spot here, we now understand most likely to be the core of, well, it is the core, most likely powered by a supermassive black hole. And by some details that I'll gloss over, it can generate actually a very powerful jet. So if you recall one of my first figures of the cluster of galaxies, I said that there was a galaxy producing a jet. Well, here's a close-up view of it. And one of the strong motivations for some of this early interferometry work was to try to peer into the cores of these galaxies and understand all of these processes. One of the other things that became apparent is if you actually tracked the motion in the jet, it appeared that parts of the jet could be moving faster than the speed of light, which actually we now understand it to be simple geometry, but at the time it was very puzzling because things aren't supposed to be moving faster than the speed of light. There's also, and this sort of goes back to the no free lunch theorem, because interferometers are largely holes, or they're very holy telescopes, that implies that we're not collecting a lot of light, which means sources have to be very bright. And I won't get into all the technical details, but there's a problem with making a source very small and very bright. And effectively, nature has some escape valves. The formal name is an inverse Compton catastrophe. But if you try to build a very compact source that's very bright enough to be seen, it shouldn't be possible, or at least the very simple initial estimates were that it should not be possible. So one obvious question is, well, maybe there's not one source there, there are two. You'd really like to resolve what's going on deep in the core, but you can't, at least not on terrestrial baselines, and therefore you go to space. So the early motivations for space-based interferometry were precisely to get higher angular resolution. And this very suggestive picture is from the VOBI Space Observatory Program, VSOP, later renamed HALCA, which was a Japanese-led 8-meter diameter antenna. And by now you understand the basic concept. Here are a bunch of antennas on the ground. There's one flying in space. As long as you can capture the signals at each antenna, and in this case, for the space-based antenna, you actually beam them back to Earth. You then add the appropriate delays. You can synthesize an effective aperture that is a few Earth diameters in size. This was the Japanese effort. The Russians flew something similar called Radio Astron. It was a 10-meter diameter. In fact, this was very recent. Only recently did the Roscosmos lose contact with this antenna. They're still actually hopeful that they can get it back, but it's been operational until very recently. And as you've probably already read, that is in principle capable of synthesizing a telescope that's comparable to the Earth-Moon distance. And I will not go into the technical, or I won't go into the astrophysical details, but it's interesting in both cases. There are still sources that are unresolved. That means they appear compact. And that tells us something about the astrophysics of what must be happening deep down in the cores of these active galaxies that are almost certainly powered by supermassive black holes. Okay. Let's look now toward the future and a couple of very exciting possibilities. So these missions were motivated by higher angular resolution. What are a couple of other possibilities looking toward the future? Well, the black hole, the Event Horizon Telescope has made a lot of press recently, and this is the picture in the upper right again. At the risk of telling you what you already know, a black hole is simply a volume that's disconnected from the rest of the universe. And the event horizon is that boundary between what's inside the black hole and what's the rest of the universe. And we often call it, we often describe the size of the black hole, or the size formally of the event horizon, by either what's called a gravitational radius or Schwarzschild radius. Schwarzschild after Karl Schwarzschild, the first person to write down these equations. And it's a very simple equation. It's the mass of the object, Newton's gravitational constant, and the speed of light squared. And if you could take the sun and somehow compress it, a solar mass compressed into a radius of about 3 kilometers would then be a black hole. So that just gives you a scale of how compact these things can be. If you look up in the night sky, which you can actually see lots of stars from dark skies in Arizona, and less so from Los Angeles, this is a view of the center of the Milky Way galaxy, and the stars there circled are some of the important stars in the constellation Sagittarius. People have made careers out of trying to peer closer and closer to the center of the Milky Way galaxy, our home galaxy, quite obvious, for obvious reasons. And there have been 2 groups that have really pushed on this using large actually near-infrared telescopes. One of the other aspects is all of these dark things here are actually clouds of dust that are obscuring the light, the starlight behind them. So you have to actually move to the infrared in order to see into the center of the Milky Way galaxy. So these are stars. This is a movie or an animation put together by the UCLA group. There's a similar group doing work out of Germany. And if this movie plays, what you'll see is the orbits of the stars. And what you'll notice is that the stars are clearly orbiting something. Particularly this star right here labeled S02 is clearly on an orbit. S019 has clearly tracked through, has clearly bent, its path is clearly bent. In many cases, these are not straight lines. And again, very simple physics, F equals ma. In order to change the path of an object, you need to exert a force. And in this case, that means you need some gravity. And you can work out, there are a couple of different lines of evidence. I'm showing you one. There's some radio interferometry evidence. There's got to be something at the location of this star symbol that is about 4 million times as massive as the sun, and yet it doesn't shine. And that in and of itself is an amazing statement. So the least bizarre explanation for what sits at the center of the Milky Way galaxy is a supermassive black hole. And now you can run through, well, okay, how big would this supermassive black hole appear in the sky? What angle would it be? and we take the size of the short shield radius and we divide by the distance to the galactic center and we get an angle. And by now you've probably already read it's a very small angle. It's 10 to the minus 10 radians, or about 20 micro arc seconds. So again, just remember, the human eye sees 1 arc minute. An arc second is 1/60th of an arc minute. And now I'm talking about micro arc seconds, so millionth of an arc second in size, or 10 millionths of an arc second in size. And that's where the Event Horizon Telescope was born, the concept of how do you get 10 micro arc second resolution? Well, you build a telescope that's the size of the planet, and you can see here the various symbols indicating the antennas that were used to build this interferometer, or this synthetic aperture. I will gloss over for reasons now of why this particular wavelength was used, but effectively you end up getting the appropriate resolutions that are needed to resolve the scale of an event horizon, say for the supermassive black hole at the center of the Milky Way galaxy. Now, in fact, the picture is not from the Sagittarius A star, the object at the center of the galaxy. It's from a nearby massive galaxy. It's 1,000 times farther away, but the supermassive black hole is 1,000 times brighter. So as you peer into the center of this galaxy in the Virgo cluster called M87, you end up with this image, this impressive image, which again is produced by an interferometer about the scale of the Earth. However, by this time you should also appreciate this is a very sparse aperture, right? This is a very holy telescope. So you might ask the question, is there a way that we could make this telescope, this synthetic aperture, more complete? Could we fill it in? And one obvious way is, well, we build more telescopes on the ground. But even then, here is the visibility, here are the visibility measurements for the Event Horizon Telescope, or a representation of them from a forthcoming paper by Daniel Palumbo and colleagues. And the 2 different colors represent 2 different wavelengths at which the EHT might observe. But you see that even after several hours of observations, the EHT synthetic aperture remains very sparse. And they're limited because the telescopes are anchored to the ground, they're anchored to the Earth, and they can therefore only move as fast as the Earth is moving. So if we look at a very short snapshot, suppose we look at 10 minutes of time, and again, just as a reminder, the coordinates here are the separations between the antennas measured in wavelengths. This is what happens if you have antennas on the ground. What if you put a telescope in space orbiting the Earth? Well, a spacecraft in low Earth orbit has about a 90-minute orbital period. So over the course of even a few minutes, you trace out many, many separations between the one space-based antenna and the other antennas on the ground. So you can immediately see, if I compare a very short duration image or very short duration snapshot from the ground-based EHT versus adding just one antenna that's orbiting the Earth, the synthetic aperture becomes much more filled, or much more complete. And this is distinct from where I started. I started by saying I want angular resolution, right? I want to build a bigger and bigger telescope to see smaller and smaller things. And here it's less about building a telescope that can see smaller and smaller things and building a more complete telescope that motivates a potential space mission. So if we had an antenna that works at EHT frequencies, but was orbiting the Earth as opposed to being anchored to the Earth, one would get a much more complete picture and much more complete synthetic aperture, and therefore potentially a much higher fidelity image. It'd be a much better performing synthetic aperture. That is one motivation based on very recent results of why you might want to go to space to do this interferometry thing. The other possibility for going to space, and this is the same for other branches or other wavelengths in astronomy as well. If you look at very long wavelengths, in fact, the Earth's ionosphere becomes opaque again. So there's some radio radiation that does not make it to the ground. And in fact, some of that is produced by the sun. So what I show you here is, on the left, this is a so-called dynamic spectrum. So it's essentially how bright the sun is as a function of frequency on this axis and time on the horizontal axis. And the different colors represent the different brightnesses. But what you can see is that there is this curving line down, or set of curving lines down like this. This is a particular kind of radio emission that was described, I don't know, 60 plus years ago, called type 2 emission that comes out of the sun. And we suspect that it has something to do with shock waves that are generated by massive explosions at the sun, but we don't actually know. And in fact, these particular data that I'm showing here were gathered by a single antenna in space. So you can tell that the sun is producing radio emission, but you can't actually tell where it originates. You can't actually tell even which side of the sun it originates. I think in the interest of time, I'll skip over some of the technical details, but essentially the question here now becomes, could we figure out where relative to the sun is this kind of radio emission being generated? It's being generated, we think, by shocks, but we're not entirely sure. And those shocks, we think, are generating energetic particles that actually lead to the radio emission. So the idea here is one of the other motivations for a future space mission is to construct a synthetic aperture to look at the sun so that we can figure out where is the radio emission, by which we need to make an image, or we need to have some angular resolution to tell where the radio emission is happening relative to the sun. So this is the sunrise concept, for which I'm actually the project scientist. It is if you've counted, there are 6 spacecraft shown here. It's an interferometer of only 6 spacecraft, but it synthesizes an effect, or will, if it's selected by NASA, synthesize a synthetic aperture. And because there are 6 antennas, one of the reasons, well, the reason we're looking at the sun is it's in some sense a very holy telescope, and therefore it is only sensitive to the very brightest objects in the sun, as the brightest object is easy to see with 6 antennas. Again, the motivation here, partly it's angular resolution. We could build a the spacecraft here are separated by about 10 kilometers, but the motivation to go to space is not to build a 10-kilometer scale telescope. It's to get above the Earth's ionosphere, get above the part of the Earth's atmosphere that is opaque and we can't see to the ground. Just as a way of wrapping up, here's the actual spacecraft. The spacecraft is very simple. Well, the antenna is very simple. It's just really almost sort of it's 2 pairs of basically wire. And the spacecraft itself is no more than 10 centimeters by 20 centimeters by 30 centimeters, which is otherwise known as a 6U CubeSat. And if this movie plays, this movie will make sense now from some of the orbitology that we're doing and how we build up the synthetic aperture. So again, if selected by NASA, here is the sunrise constellation that would be orbiting the Earth, and the sun is in the background. And now we zoom in to the actual constellation. And this actually goes back to some of the points I was making earlier. We are not attempting to control the locations of these spacecraft or antennas. We only put them on orbits and then monitor where they are. We do not try to, well, more or less do not try to control them. And what you can see here is the different orbits. You can see the different separations between the spacecraft. And what will happen in a moment is that we will start to construct the synthetic aperture by measuring the distances between the individual antennas and projecting those onto a plane to indicate how big the actual synthetic aperture is. I think in the interest of time, I'll not let the movie play out, but you can see here's the start of trying to illustrate this concept. And actually, 2 other comments. The mission design team have these affectionate names for the spacecraft. You can also see the spacecraft are color-coded so that you can tell which baseline corresponds to which pair of antennas. So I won't let the movie play, but you can, I guess you're going to have these slides available so you can see the whole movie, and you can actually see how the synthetic aperture gets formed from the various combinations. And then as the spacecraft move, the synthetic aperture changes, but we only need to know where it is. We don't actually need to control them. Okay, I should acknowledge, I've spent a lot of time talking about radio. You can actually do this in the optical. People do this in the optical. So you see on the top row here are 3 optical interferometers. Now, an important difference, when you go to shorter wavelengths, it's no longer possible to record the signal. So what actually happens is that these individual telescopes, and you can see perhaps on the left, this is the CHAR array, the individual telescopes, what they actually do is they have pipes down which they shoot the light beams, and then there's a combining facility that you have to do it in real time, and you actually move around little mirrors on, typically what has happened is people move around little mirrors on platforms and try to adjust in real time to keep the keep the light all coming together at the same time at the same place. possibly in the future, well, there's certainly been concepts, there have certainly been discussions about how you might take this to space on the optical side, forming an optical interferometer to do things such as actually look at the surfaces of stars. There have even been concepts of extending this into the X-ray, of taking a constellation of X-ray reflectors and forming a very sharp image of a supermassive black hole. You can see that in the radio, of course, that's already been done at some level. Okay, so I hope I left enough time for questions. The takeaway summary is, in general, high angular resolution demands large apertures, and synthetic apertures can be constructed using this interferometric technique. I hope I've given you at least a heuristic appreciation for it. It depends on relative antenna separations. So we need to know where antennas are, which is especially important in the space context, but we don't need to control them. There have been a couple of space interferometry missions already, and there are exciting potentials in the future for how we might use this to look at black holes in new ways, or even opening new windows on the universe. So I'll leave it there, and this is the I believe, evaluation or the summary that Demetrius referred to earlier, and I'll take questions.
Thank you very much, Joe. We all really appreciate your time, and the wonderful presentation will be great for our students. Time for questions. If you want to have a question, by the way, please turn on your video and audio so that we can hear you.
I have a couple of questions, but I can let Junhan ask first.
Go ahead, Junhan.
Can you hear me?
Yes.
Oh, hi, Joe. Yeah, one quick question of this BLVI. Given the high data rate of, for example, EHT, what's the possible solution of, say, data transfer?
There are two answers to that. One is, and we faced this in Sunrise. One is to evaluate very carefully how much data actually have to be brought to the ground. And that goes to just the general way to structure space, at least in NASA. I of course, have no experience within ESA or JAXA. One has to specify very carefully what the science goals are and how that translates to the amount of data that is needed. So one aspect is just a very careful evaluation of what is the science question, how much data actually need to be brought to the ground. The other is that there are techniques such as optical communications, which are getting proven out now. There have been flying demonstrations of optical communications. And at that case, you start getting into, I think, certainly from low Earth orbit, easily tens of gigabits per second. So you start to get to, I don't actually know off the top of my head, don't remember what the EHT data volumes are, what they would imply, but you can imagine much higher data rates than have been possible in the past. And I think actually to go back to one of the plots that I showed, the motivation for going to space for an EHT-like concept would be to fill in the visibility plane, or fill in the synthetic aperture. You could ask the question, do I really need to bring down all those data? For instance, could I do 5-minute, go on 5 minutes, go off 5 minutes, go on 5 minutes, and collect, say, only on a 50% duty cycle, but bring down enough data to get a better aperture? Those are the kinds of questions that would need to be addressed.
Thanks.
Hale?
Thank you, Joe. That was really great. I have a couple of questions. One is about the positional accuracy if we wanted to go this route with the EHT. You talked about 3 meters for Sunrise. That's probably a wavelength dependent requirement.
You are correct.
What are some, can you give us some order of magnitude requirements that we would have to face with the EHT?
Sure, and actually this is general, not just to interferometers, but a rule of thumb is that in order to work as a telescope, in order for the light to come together in the same place at the same time, the telescope has to be smooth to, people use different numbers, but something like 1/10 of a wavelength or 1/16 of a wavelength or 1/20. And different people have different rules of thumb, but it's something of order It's something of order a tenth of a wavelength or better. And in fact, the 3 meter requirement for sunrise is motivated by the fact that our wavelengths are like 30 meters and longer. So we're working at very large wavelengths. We don't need precise positioning. You can work out for an EHT-like concept, one would need sub-millimeter positional knowledge. Again, knowledge. I think that is beyond the current state of the art in terms of determining spacecraft positions in low Earth orbit. But that's also an area of interesting technology. If you imagine, in low Earth orbit, you can use GPS quite easily. Would there be future GPS technologies or combinations of things that would allow the positional accuracy, positional knowledge, good enough to be able to do an orbiting antenna? And I think it's an interesting question. I don't know, say a decade hence, how well we could do in terms of positional knowledge in low Earth orbit. And it may be that the EHT or an EHT-like concept would be stressing for, or it would be one of those things that would actually push future determinations of spacecraft positioning.
Thank you. If I may ask a second one, I think you talked about this a little bit, but maybe I missed it. What is the primary science goal for Sunrise?
The primary science goal is there are the particles that are accelerated, and you might imagine accelerated. The Pavlovian response, particularly among radio astronomers, is all you need is a little bit of a magnetic field and some accelerated particles and get radio emission. So there's this particular kind of radio emission that is clearly generated by coronal mass ejections. It's clearly connected somehow, or it's at least correlated with particles being accelerated by these coronal mass ejections, these massive eruptions of plasma. But there are 4 broad classes of models of where those particles might be accelerated. And the objective behind Sunrise is to get good enough localization, which we're doing via imaging, good enough localization to be able to say, are the particles being accelerated at the nose of the shock, on the flanks of the shock, in the middle through reconnection? And it's fascinating. This is doing it with our star, the nearest star as a laboratory. But some of these questions are also applicable to various other parts of astrophysics, such as how do supernova remnants or how do clusters of galaxies accelerate particles.
Indeed, I just covered shocks in my high energy class today. So.
Yes.
More questions for Joe? I have a quick one about Sunrise myself. Again, about positional accuracy. You said 3 meters. How do you get 3 meters? It seems like a big number, but you want it absolute more or less, right? You don't really care about the differential position. How do you get 3 meters in low Earth orbit?
Well, first off, Sunrise, if selected, would fly actually in GEO, just above GEO. And we would actually be using GPS. So we use GPS to determine the locations, the positions of the spacecraft, each of the 6 spacecraft. And that's part of the GPS signals are captured on the ground, captured on the spacecraft and then transmitted to the ground. And this is one of the powers of interferometry. And I think it would be, one would have to exploit it to do a future space-based EHT as well. You bring the signals to the ground and you do post-processing of figuring out where the antennas are later, and then adding the appropriate delays, taking into account the separations.
Yeah, the GPS constellation is low Earth orbit, right?
Say again?
The GPS constellation is low Earth orbit.
GPS is actually sort of middle. It's, I want to say 10,000.
Yeah.
Yeah, so we are not, well, there's a technical detail there, but it's above low Earth orbit, but it's below GEO.
Yes, and so do they transmit that information outwards to the level that you can actually do that? Just curiosity, I know nothing about what happens outside of the GPS orbit.
Right. Well, the GPS what we are exploiting is the GPS spacecraft on the other side. So I don't know if you can see my cursor, but if you imagine the GPS satellites are all orbiting the Earth, when they're on the other side of the Earth, transmitting toward the Earth, some of that signal still spills past the Earth, and we're picking up the stuff that essentially spills past, and it's weaker because it's farther away, but it's still strong enough to be detected and used.
And you only meters, right?
Yeah, and in fact, NASA is currently flying a constellation called the Multi-Scale Magnetospheric Structure, if I'm remembering correct, MMS, which is an even higher orbit or farther away, and they are also picking up GPS right now.
Very good. Any more questions for Joe? Okay, thank you very, very much, Joe, for this wonderful presentation. And for everybody,
my pleasure.
Please fill the feedback form, and hope to see everybody in the next PIRE webinar. Thank you.
Thank you.